So let us now consider the design of NVIDIA Tesla GeForce 8800 GPU. So there are many kinds of GPUs. NVIDIA itself has released several GPUs after this version. So this version as of now is at least around 5 years old. But nevertheless, be it NVIDIA, be it Intel, the basic concepts are more or less similar. So let's just overview the basic concepts, even though note that the designs themselves can change. So in this case, we first have the host CPU, which via a bridge, which is also called a bus, will actually, access the GPU. So pretty much, this is where the GPU begins. So we'll learn much more about bridges and buses and so on. So a bridge is essentially some sort of a device that allows the GPU to talk to the CPU, the GPU to talk to memory, the memory to talk to the CPU, right? It's something that allows us to do that. What exactly is a bridge? We'll learn more about it in the next chapter. For the time being, let's live with this abstraction. So the first thing is we have a host interface. The host interface interacts with the host CPU, gets work from it. Subsequently, there are different units of the GPU. So there are first some traditional units whose job is to actually do the graphics oriented tasks. So the first is the vertex. So if you would see the vertex processor, which processes shapes, objects, rules, and effects. So essentially the first part is a vertex processor, which does all the vertex work. After the vertex processor, we had the rasterization phase. So we then have the raster phase and essentially the fragment processing engines. So all of this part is essentially becomes the traditional GPU, which is exactly what we have seen in the previous slide, which is this slide. That this is the work of the traditional GPU: vertex processing, rasterization, fragment processing, and frame buffer processing. So all of this work is done in this part of the circuit. The GPGPU nest, the general purpose character of a GPU, right, comes from this particular block, which sort of makes a general purpose. And this block is called the job of this block is to distribute the compute work. So as I said, GPUs had a lot of processors and a lot of circuitry to basically mainly process and compute graphics data. But then architects realized that a lot of that circuitry can be in a sense reused to do traditional computations such as linear algebra, matrix multiplication, matrix inversion, all of that. And that is managed by this compute work distribution unit, whose job is to actually access the computational part of the GPU. So mind you, this part of the GPU is shared between the regular graphics tasks which come via this route, right? Which essentially come via this route and this route, and the compute work which comes via this route. So basically, if I let me just clear off the ink. So pretty much above this, we have a certain differentiation of the source of the work. So what we have is that above the line, we can have different sources of work, and of course the pre-processing is there. Below the line, it is somewhat more generic, even though not 100% generic. So we have 8 TPCs. So a TPC is defined as a texture processor cluster. So let me see. So it means it has units to process the texture. So once, if we just go back once again, we will see that the fragment processing part, this part can also add little bit of texture to the different fragments. So also it has regular processors. So both of these are required in graphics jobs, as well as the processors are required in general purpose jobs. So this particular GPU has 8 TPCs, but of course in other GPUs can have more TPCs. Each TPC has 2 SMs. And SM is defined as a streaming multiprocessor, which means that streams of data come from the top, from the host CPU or from the memory, and the SMs process them, and SMs themselves have multiple processing units. So the nature of the data is streaming in the sense like, water streams down a river. We have instructions and data streaming down. So an SM is a streaming multiprocessor. So a TPC contains two SMs, where one SM contains multiple processors, and then they have a texture unit whose job is to do additional texture processing. All of these 8 TPCs are connected via an interconnection network. So note that this is an important structure, so we'll study more about it after we finish GPUs. We'll look at interconnection networks. So they can be interconnected in many ways. We'll look at the different ways, but let's assume that in any network, any SM can communicate with any of these modules over here. So we have 6 DRAM modules, so where one module can contain a fair amount of graphics DRAM. And there is an L2 cache between the interconnection network and the DRAM. And also there is an ROP. An ROP is a raster operations processor, which does additional processing for raster operations. Right, so that is what an ROP does, that it's a raster operations processor. And also we have a traditional part of the memory hierarchy with 6 L2 caches, the address space of course being divided between these 6 and individual DRAM modules. So this DRAM is separate from the system memory, which is also DRAM, but this is sort of the GPU part of things, GPU side of things. So the GPU has a nice division between the traditional GPU features and the new features, which are the compute features. So both of them are supported. So that is the greatness of the general GPGPU concept, that you can actually do both. So let's look at an SM. So let's go back and let's look at a TPC. There are 8 TPCs, and inside a TPC we have multiple things. So let's see. We have a geometry controller. So this is again part of the graphics part. So it converts operations and basic shapes to multi-threaded code. So the great thing about graphics processors is that we actually, so we don't give it very low level instructions. The instructions are somewhat at a higher level, and then low level instructions in the PTX, typically in the PTX instruction set or other internal, representations of low level instructions are used. So essentially based on the operation, a set of instructions here are created, and these set of instructions are conveyed to the processing units. So it is essentially first conveyed to the SMC. The SMC is an SM controller. So it schedules instructions on the SMs, right? So there are 2 SMs in every TPC. On the SMs, it schedules the instructions. So one SM is, as described, a streaming multiprocessor. So it has many compute units. So let's see. The first thing is that it has 3 caches. So this is the memory part of it. So it has these 3 caches, and then these are all the compute units. It has a little bit of shared memory for all the compute units to communicate between each other. And it also has a texture unit whose job is almost exclusively to process texture information. And the texture unit inside has a texture L1 cache for its own work. So what we are mainly concerned with is the caches here and the compute units. So broadly speaking, there are 2 kinds of caches. So the caches are somewhat like this, that we have an instruction cache. So the I cache over there is an instruction cache. So we always need an instruction cache. So this is over there. So 1 instruction cache per SM. But since it is it's broadly a vector kind of processing is happening. So we'll see exactly what's the model, but the model is broadly, a vector kind of processing. So that's the reason the instruction cache can actually be highly efficient, because the same instruction actually ends up executing in the entire SM, in all the SPs and the SFUs. The empty issue is a special unit like the SMC, so it's a multi-threaded issue unit that coordinates the actions across all of them. And the C cache is one more cache, which is a constant cache. So a lot of algorithms actually use, constants, for example, E, pi, and so on. So all of these constants can be saved here in the constant cache, right? So beyond these caches, actually one SM has 8 SPs. SP is a simple streaming processor core. So mind you, this is a very, very simple core. It is far simpler than the in-order processor that we have designed in chapter 9. It might be at best a one-stage or a two-stage pipeline. So, it's a very simple device, and its main role is to fetch an instruction from the I cache, do some very basic decoding, do the execution, and essentially send the data to shared memory. And some graphics processors also have graphics registers. I don't want to go into all of those details. But let's just think of it as something that pulls data from, pulls instructions from the I cache, pulls data from the shared memory or the DRAM, does some processing, and the data goes back to the shared memory and the DRAM. So going back to the previous diagram, each SM will essentially pull data from here and process it and send data back. Or it can even send data back to system memory. So there are different pathways possible. So we'll not explore all the pathways, but essentially it's something, the main advantage of streaming is that you are mostly looking at data once. So you take a look at data, you process it, then you take a look at some more data and so on. So you typically don't look at the same data item twice. So if you think about it, all of these simple cores that we have over here, we have 8 SPs per SM. And we also have 2 of these SFUs, which are called special function units. So SFUs as compared to SPs are fairly advanced in the sense that one SFU can actually take in 4 instructions per cycle and execute them simultaneously, right? At least in this version of the GPU. Sorry, not 4 instructions, not, yeah, 4, it can take, 8 instructions in 2 cycles. So that's what it can do, and it can execute them simultaneously. In addition, what it can do is that it can compute the results of complicated functions like transcendental functions and log and so on. So its processing powers are much, much more than these simple SPs, because SPs are pretty much good enough only for add, subtract, multiply, and divide, whereas the advanced functions, trigonometric functions and others, can be handled by the SFUs. So if we just count cores, right, irrespective of how many instructions they can process, then we have 10 cores in each SM, 10 times 2, 20 cores per TPC, right? And we have 8 TPCs, so total we have 160 cores, right? Even in this, relatively old graphics processor that we are seeing, which is also pretty simple, we have roughly 160 cores, and 160 cores is, fantastic. We can do 160 additions simultaneously, and we'll see actually slightly more than that. But this is a fantastic thing that we can do, which is that basically uh, we can enjoy a massive amount of parallelism. Actually, I take back this 160 additions at the same time, because calculation is slightly different, but we will see the calculation when we go to the next slide. But the main thing is that we have 160 cores active at the same time, and which means that 160 instructions are being processed at the same time, which will give us a massive amount of parallelism. After this, the texture unit does the texture processing, but that is not really important for us at this stage. We are mainly concerned with the SPs and the SFUs. So the computation on the GPU goes on like this. So the GPU groups a set of 32 threads into a warp, right? So of course, 32 is not a number written on stone. So it can be 32 for one GPU, 64 for one more. But let's assume, a number that is, 16, 32, or 64, some power of 2. So in this case, 32 threads, they are grouped into a warp. And each thread has the same set of dynamic instructions, means that this is, it's exactly SIMT, which means the instructions are exactly the same for all the threads, right? So, all 32 threads, the instructions are exactly the same, even though the data is different. So, in a sense, it's also a SIMD kind of computation, but it's just that since it's across threads, we call it SIMT. And so basically 32 threads and their data sources are different, so they work on different pieces of data. And very, very similar to what we have studied on vector processors, and very, very conceptually similar, is just that instead of multiple functional units, we have multiple threads. Similar to vector processors, we have predicated branches. So essentially, we don't have any branches per thread, and it's never the case that different threads actually fall out of sync with each other. So for all of them, we just execute them instruction by instruction and finish off at least n instructions for each warp. So what the GPU does is that it maps a warp to an SM. So the warp is a set of 32 threads, and one SM is essentially mapped a warp. Alright. So each instruction in the warp executes atomically, which means that either it fully executes or it doesn't execute at all to an external observer. All the units in the SM first execute the ith instruction of each thread in the warp before considering the I+1th instruction or an instruction from another warp. So it is possible that at one point of time, multiple warps can actually be scheduled on an SM. So the SM will, maybe consider warp 1 and execute its ith instruction fully before even executing the I+1th instruction in warp 1. Then it will consider warp 2, execute some of its instructions, again for all the threads within warp 2. Then come back to warp 1, execute a few more instructions of warp 1. But the important thing is that the execution of an instruction is atomic. In the sense, for all 32 threads will essentially progress by the same number of instructions before the warp gets swapped out and another warp comes in. So this kind of a model is a single instruction, multiple threads kind of model. So let us look at an example computation on a GPU. So let us assume we have a SM multi-threaded instruction scheduler, and this is the schedule it produces. So let's say we start out with warp number 8, we execute instruction 11. So after executing one instruction fully for all the 32 threads, the GPU is free to choose another warp. So let's say it chooses instructions from warp 1 and instruction 42. And then it again chooses instructions from warp 3 with instruction 95. After that, it chooses other warps, but it does not choose warps 1, 3, and 8. So after that, let's say it comes back and chooses warp 3 again. So in this case, since it has already executed instruction 95, it will start with instruction number 96 and execute 96 fully. And then again the GPU might decide to go back to warp number 8, and since instruction 11 was executed, so it will execute instruction number 12. Finally, it might decide to again look at warp number 1, and since instruction 42 was executed, it will now execute instruction 43. Now let us look at how computations happen in a GPU. So we pretty much, the throughput of a GPU is decided like this, that we execute a new instruction every 4 cycles. So the throughput, so mind you, an instruction means something else in the context of a GPU. So what an instruction means is that given a warp has 32 threads. So all the 32 threads execute one instruction each, the same instruction, the ith instruction, and the rate of such kind of an execution is once in every 4 cycles. So the way that things work is that if you would go back to the diagram of one SM, so inside an SM there are 8 SPs and there are 2 SFUs. So on the SPs we schedule 8 threads that run on the 8 SP cores. Of course, one thread running on each SP core once every 2 cycles, right? So once every 2 cycles we schedule 8 threads, and so then they can execute one instruction each. So basically in 4 cycles we can execute 8 times 2, 16 instructions. So then for the 2 SFUs, so the SFUs can actually, one SFU can execute 4 instructions, it can take in 4 instructions in the same cycle. So basically if you have 2 SFUs, right, one SFU can take in 4 instructions every cycle. So if you have 2 SFUs, they can take in 8 instructions every cycle. So SFUs are also scheduled once every 2 cycles. So this means that since once every 2 cycles they can process 8 threads, so in 4 cycles they can process 16 threads. So we have 16 plus 16, 16 coming from SFUs and 16 coming from SP cores. So the sum total is 32, which means that every 4 cycles we can pump in 32 instructions into each SM, right? So it would be better to say we can execute a new instruction for a warp, such that it's clear. It's not a single instruction, it's a single instruction for all 32 threads. So that actually makes a total of 32 instructions. So if you think about it, the throughput of each SM is 32 instructions. It depends on how you count. So if we count the total number of instructions, it's 32. But if we count it from a program point of view, it's 1. So it doesn't matter, but if you look at total instructions, then it's 32 for every 4 cycles, 8 instructions per cycle per SM. So threads, so moreover, threads in a warp can share data through the SM specific shared memory, just in case they're accessing some shared, a shared data structure or something. So the shared memory that is there in each SM can be used to share data between threads of the same warp. So a set of warps are grouped into a grid, and different warps in a grid can execute independently. So what we do is that each warp has a set of threads, and a set of different warps are grouped into a grid. And different warps will not communicate through the SM specific shared memory, but they will communicate through global memory, which is essentially the DRAM modules that are either in the GPU or off-chip DRAM modules. So just to give you one more idea of the net throughput that we are talking about, so here what we have said is 32 instructions per 4 cycles per SM. So this is essentially 8 instructions per cycle, right? 8 instructions per cycle per SM. So if we have 8 TPCs and each TPC has 2 SMs, so that is 16 SMs. So in a GPU, even a GPU that is slightly old, in this case NVIDIA Tesla, so it can execute 8 times 16 or 128 instructions in parallel, at the max in a given cycle, which is fantastic. This is a massive amount of throughput, and so in general the multi-core processor will not have this much of a throughput. So mind you, these instructions are all very simple. They're not very complicated at all. Simple add, subtract, multiply. But we can use this to actually process a lot of data, and also generate and render very, very complicated scenes. But it should be understood that the IPC of a GPU is actually very high, and in this case the IPC is 128, which is actually genuinely very, very high. So that's the reason GPUs are very power consuming devices. But again, for high intensity graphics, high fidelity graphics, and playing games where multiple characters and guns and bazookas, everything zooming around, or watching movies, creating movies, GPUs are should definitely be used and are definitely used. So now let's look at a very simple program that we'll write on a GPU. So mind you, this is just the start of, this is just the tip of the iceberg. So a lot of programs can be written that work on GPUs, and there are also different kinds of flavors of GPU languages. So one of the most common flavors is CUDA, called the Common Unified Device Architecture. So this is very popularly used, particularly in NVIDIA GPUs. So it's a custom extension to C++, where there is a separate CUDA compiler that separately compiles the code for the GPU, and you have a separate CPU compiler that separately compiles the code for the CPU. So in the context of a GPU, we define the term called a kernel, which is a piece of code that executes in parallel, on the GPU, of course. So we define two concepts over here. The first is a block. A block, or a CTA, called a cooperative thread array, is something similar to a warp in a programming language terminology, in the sense that threads in a block are supposed to execute together, same as the threads in a warp. And the blocks together are grouped in a grid. So similarly, we defined a grid of warps. So in this case, we are defining a grid of blocks. So a part of the code executes on the CPU, and a part of the code executes on the GPU. So let's look at a simple CUDA program. So in this case, this is similar to the example that we saw with SSE. And here the idea is that we want, to add two arrays, A and B, so which are essentially vectors, and produce a result vector C. So we want to add a vector A and vector B, and produce vector C. So this particular program is written is written in C using the CUDA API. So one more API is called OpenCL, which the AMD GPU uses. So OpenCL is similar to CUDA, but of course there are differences. So let's take a look at a CUDA program. So let us first take a look at the main function. We'll take a look at the GPU part somewhat later. So in the main function, let us declare three arrays A, B, and C, each having n elements each, where n is defined to be 1024. So fairly large, arrays. Well, not that large on a GPU scale, but large enough for us to see what is the benefit of actually running it on a GPU. So instead of 1024, we can make it a million. So I will ask, I would ask readers to consider a much larger array, and then they can see the real benefit. But that's okay. For the purpose of demonstration, it's fine. So now let's do one thing. Let us declare the corresponding arrays in the GPU. So mind you, these arrays are being declared in the CPU, but they are not being declared within the GPU. So let's do one thing. Let's declare them in the GPU. So let us now see how we need to create some amount of space within the GPU to store a copy of these arrays A, B, and C. So the function in CUDA to allocate space within the GPU is CUDA malloc. So what CUDA malloc does is that it allocates space within the GPU, and so it basically allocates it at these pointers. If you would recall, we had defined GPU A, GPU B, and GPU C as int star pointers, means that they point to integer arrays. So what we do is that we send a pointer to these arrays, to the CUDA malloc function, and of course they need to be they need to have the type void star star, means pointer to a pointer of objects of type void. So void star means a pointer to anything. So it's an array of pointers to anything. So it needs to be typecast in this fashion to be actually sent to this function. And size is the size of the arrays. So recall that the size we had defined over here as the number of elements in the array n times the size of a single integer, which can be either 4 bytes, sometimes 8 bytes, depending upon the system. After this, so basically CUDA malloc creates space within the memory space of the GPU. Once that is done, we initialize the arrays A and B. We fill them with data, because finally we need to add the vectors A and B to get the vector C. Then what we do is that we transfer the data, which is essentially array A, into the GPU. So that is done by transferring array A to the pointer GPU underscore A, which is basically a reference to the array where this space GPU underscore A is actually stored inside the GPU. Size is again the number of bytes, which is the size of the array. And this is a flag which tells us that we are doing a memory copy from the host to the device. In this case, the host is the CPU and the device is the GPU. So data is flowing from the CPU to the GPU. Alright. And similarly for the array B, we transfer the contents of array B to GPU underscore B. What this basically means is that GPU underscore B is the place where the array is stored inside the GPU, and we have already created space for it using CUDA malloc. So we transfer size bytes again from the host to the device. Once we have done that, the next step is to invoke the vector addition operation inside the GPU. So what we do is that we basically invoke the vector add operation, and the way the vector add operation is invoked is something like this. So vector add is the name of the operation, right? So it's the function. But the way that the function is called is somewhat different. It's a special way of calling the function. What we are doing is that within these 3 less thans and these 3 greater thans, we are specifying the number of threads in a block and the number of blocks in the grid. So we are sort of creating a 2D structure over here where, let's say, so we have n elements. So in principle we are creating n threads, where the job of one thread is to add one pair of elements. So essentially we are creating a matrix of GPU threads which has n by 32 rows and 32 columns. So this is a matrix of GPU threads where each cell represents a GPU thread, and the job of this cell is to basically add 2 elements within the arrays GPU A and GPU B, right? Perform an addition operation and save the result in GPU C. So essentially this is the same as for all I, essentially add AI plus BI and assign the result of AI plus BI to Ci. And of course I varies from 0 is less than I, which is less than n minus 1. So essentially I can take n values. So the way that we are invoking this function is different. It's not a part of C syntax, but that's the reason this program needs to be parsed by a CUDA compiler first, such that it can generate the GPU code, and subsequently a C compiler will generate the CPU code. And both the codes, the CPU code and the GPU code, will work together. So this vector add function is essentially a kernel whose job is to do the addition inside the GPU. But mind you, this is not a it's not a built-in function of CUDA. So it is something else, and I'll come to what that something else is. So in this case, but the most important thing that the user should basically look at is this n by 32 and 32, where essentially we're dividing all the threads into a matrix. And so this will help us create, warps and a grid, right? So let us now look at this vector add function, which was there on the previous slide, but we skipped. So here it is. So this vector add function actually we have written. It's not something that CUDA is providing as a built-in, but the way that you divide. So this is the GPU kernel. This is the part of the code which will actually execute on the GPU, and the rest will execute on the CPU, of course. Most of it. See, so the way we define it is that it's a global function, so underscore underscore global underscore underscore. This function does not return anything, so it's a void. And it takes three arrays as input. It takes GPU A, GPU B, and GPU C. And the final aim is to ensure that GPU C is equal to, GPU A plus GPU B. So this function we have written, we always need to write one such function because CUDA does not have that many built-ins. Also, it tells us how to write a function, right? We might instead of addition, we might be doing some other operation. So in any case, we always have a underscore global identifier. Then we write a function. So the first thing that we do within this function is that we compute the index, right? So the index is basically, when in an array, the same way that we were using myID in our OpenMP and MPI programs, index refers to the index of the element, which element it is. So it's very easy to compute it. So every thread ID, so these things are all built in, right? So every thread has a thread ID. It has an X coordinate. So it is the ID of the thread within the block plus the block ID of the block multiplied with the dimensions of the block. So what we are doing is that we are taking our threads and we are grouping them into blocks, right? So one more block. So ultimately the ID of a thread is the ID of the block multiplied with the size of the block, which is this part, plus the ID of the thread within the block. So this is exactly what this is trying to specify. So this is how we get the identifier, the global identifier, the index. After that, we just perform an addition, which is exactly what the GPU is supposed to do. It's an element by element addition. So we basically take the IDXet element and for A, B, add them together and save it in the IDXet element of GPU underscore C. So for those who have seen all the parallel programs that we have written in this chapter, starting from OpenMP to something which was inspired by MPI, to one of the raw parallel programs we wrote for an SC machine, to one more that we wrote for a WC machine, all of them worked in pretty much the similar manner, where we just create multiple threads. Each thread has a thread ID, and the thread ID tells us which elements we need to operate on. We operate on those elements, and of course this function is spawned in parallel for each of the threads. So this vector add function we have written, and so thread IDX, block IDX, and block dim are all CUDA built-ins. And finally, we are doing the addition. So once the CUDA compiler will convert this to appropriate GPU code. Once we have called vector add, so then after this function, it means the result is there within the GPU. So what we do is we again transfer the contents from GPU underscore C to C, which basically is from the device to the host. So device is the GPU. So from the GPU to the CPU, we initiate a command to transfer the data and of size bytes. So it again comes within the array C, which is the final result. So now that we have computed the final result from the GPU and we have gotten it into the memory space of the CPU, what's left? Well, what's left is a final cleanup. So we free the space within the GPU. So we call the CUDA free call, which frees up the space for GPU A, B, and C. So this is essentially the code to do a computation within a GPU and to get the results from the memory space of the GPU to the memory space of the CPU. The important elements, let me again clean this up. The important elements of this computation are basically that we define our own function, the GPU kernel, which of course first gets the ID of the element, By finding the ID of the thread and the ID of the block, we tell the GPU what needs to be done. And after that is just a matter of making the arrays, moving data between the CPU to the GPU, invoking vector add to do the addition within the GPU, and again moving data from the GPU to the CPU. So this is mostly how all GPU computations proceed. So it's in a sense fairly simple. But of course, getting a high performance implementation, as we shall, as you shall see if you study more, is fairly difficult. So that's the reason, this is just the very tip of the iceberg. But there is much more to be learnt and much more to be studied for those who are looking at GPUs seriously. Alright, let's move on. Let's now look at interconnects. So interconnects is something we have not discussed. So, but if you go back, we have always said that our multi-core, our single cores, right, within a multi-core processor are connected in some way. We have always said that, if you would recall, let me just go back to the GPU diagram. If you would recall this thing, we are saying that all the TPCs and the memory modules are connected in some way, right? Also, it is possible that I can take individual chips and create a cluster of machines, right? A cluster of servers. So again, they will be connected, in some way. So let us look at the different kinds of interconnection networks and study their properties. Again, this is very basic, but this is something that everybody should know at least at this stage. So a typical multi-core processor, this is how it looks. So the blue ones are the cores. So you can have lots of cores actually, a lot of blue boxes as you can see. So this particular multi-core processor has 32 cores. You can also have cache banks, which are essentially large pieces of SRAM memories to store parts of the address space. So you will have cache banks. And the cache banks are also distributed all over the chip. So there are elaborate protocols of accessing the cores and the cache banks, but we will not discuss that. Then we have these routing elements which essentially connect, see if you consider this small cluster of cores and cache banks, they are connected to the network. So it's sort of similar to the diagram of a city. So let's imagine a small community over here that is connected with one, big fat road. And then there are other communities that connect to this road. There are other communities which connect to this road. So similarly, you can consider this as a small community. So they are connected to the interconnection network in some way via these routing modules, whose job is to interact with the network. Simultaneously, we also have these red elements called memory controllers. So you can have 1, 2, 4 or 8 memory controllers, depends on the requirements. So the job of these memory controllers is to interact with off-chip memory, mainly DRAM modules. Since you can have many DRAM modules and since a lot of requests are going, you can have many memory controllers. So the crux is basically how they are connected. So let's look at a couple of connection strategies. So the router is the core in an on-chip network, which is also called a network on chip. Right? So network on chip is also a common term for an on-chip network, and what's even more common as an abbreviation is NOC. Right? Network on chip, and O small, N capital, C capital. So a router sends and receives all the messages for its tile. A tile is defined as a small community that the router is serving, which is not connected. There's only one connection from this small group of cores and cache banks to the network. So between them, they can have a very simple interconnect. So this is actually called a tile, a set of cores and cache banks. So router will connect this to the network. In addition, the router participates in almost all activities of the network. So it forwards messages originating at other routers to their destination. So multiple routers are connected, like this. If the message going from here to here, this router will take the message from here and again, send it to this router over here. So in a typical NOC terminology, routers are referred to as nodes, and adjacent nodes are connected with links, right? So links are network links, essentially copper wires. So the routers and links form the on-chip network or the network on chip called an NOC. So up till now, what have we seen? What we have seen is that we have seen a very, very basic NOC where essentially you have a copper wire and you have all the cache banks, so you have all the caches connected to it, right? And if I send anything from here to here, all the other caches can see, because copper is a very good conductor of electricity, so everybody can see the message. So this was called a bus. But the main disadvantage of a bus is that only one sender can be alive at one point of time. You can have only one writer on the bus. Multiple caches cannot write on the bus simultaneously, otherwise there will be interference and both the messages will be gone. This has scalability problems in the sense more than 4 or 8 processors. 4 or 8 is the maximum. More than that, no way. Right? It will simply not scale. We will not be able to send messages. So let us look at bigger networks. So bigger networks mainly have two properties. One of the properties is called bisection bandwidth. So it basically means the number of links that need to be snapped, that need to be cut, to divide an NOC into roughly 2 equal parts. Let's ignore small additive constants like 1 here and there. For example, if an odd number of nodes, right? Let's say I have 17 nodes. Then one side will have 8, other side will have 9. So let's ignore those small differences. But essentially, what is the number of links? So again, what is the minimum number of links? Not the number of links, so the minimum number of links that need to be cut to actually partition the network. So this is why is this important? Well, for two reasons. One is it's a measure of reliability. Just in case a link fails, what happens? And the other is also tells you, for those who have studied algorithms, there is something called a max flow min cut theorem, which essentially tells you the maximum amount of data that can flow from one side to the other. So let me give an example. Let's assume there is a big city like this. Let's say big city like this. They are connected with a narrow bridge. Then all the traffic from both the cities will basically flow via this narrow bridge. If the cities have roughly the same size, then the bisection bandwidth of this system is 1. This bridge, for some reason, if it breaks down, then both the cities will get disconnected and trade and commerce between the cities will absolutely stop. So in a sense, it is always possible that there can be some faults in a network and links can go down. Alternatively, even if there are no faults, still this bridge is going to get heavily stressed because of a lot of traffic. There will be huge traffic jams. So as a result, having a low bisection bandwidth means that some of the links will get really clogged, as is happening in this case. So it's a bad idea. The other property is diameter. So basically, if I consider a network, right? So let me consider a network of this type. So what is the maximum distance between any two pair of nodes? Right, distance meaning the optimal distance, the shortest distance. Well, distance between this and this is 1, but the distance between this and this is actually a maximum 2. So let me consider one more network. Sorry. What is the maximum distance between any two pair of nodes? Well, the maximum distance will probably be between this node and this node, which is 1, okay, 2 links, 1 and 2. Similarly, it's also the maximum between this and this, but in this case, it will be 1 and 2. So this is known as the diameter of the network. So diameter in our example will be pretty much from, one city over here, traverse the maximum distance and go over here. So why is the diameter important? Well, it gives you a measure of the latency, the time required to go from one node to another node, where of course we are assuming that all distances are shortest paths. So our aim is to maximize the bisection bandwidth such that no single link gets clogged, and simultaneously minimize the diameter such that it is possible to go from any end of the network to any other end very, very quickly. So in terms of network topologies, we have already seen a bus. So I'll not discuss the bus once again. So I'll discuss the chain and the ring, which are fairly simplistic topologies. So in a chain, all the nodes are arranged in this fashion. And one connects to the other, and the other one connects to the next, and so on. Well, the nice thing of this is simple, but the bisection bandwidth is really low, it is 1. And the diameter is really large, which is, if let's say I'll have to pretty much traverse n minus 1 links, the diameter is fairly large. So if you see what was our aim? Aim was to maximize the bisection bandwidth, minimize the diameter. We are not doing that. We are in fact doing the reverse. So another common topology which can be used for moderate size systems, 4, 8, 16 processors, is actually a ring. So in the case of a ring, the bisection bandwidth is 2 because we need to snap two links to disconnect the network, to split it in 50-50. So two links have to be snapped. The diameter is also not n, it is closer to n by 2 because we can either traverse this way or we can traverse the other way. So roughly, this is 2 and n by 2, roughly approximate figures, which is better than a ring, better than a chain. So a ring can be preferable in some situations, especially, when we don't have many nodes. Now let's take a look at a factory. So a factory is not a typical network that is inside a chip, but it is a typical network for a cluster of chips. So in the case of a factory, what happens is that we actually have our nodes, which are the leaves of the tree. So all the blue nodes over here are the leaves of the tree, all the blue nodes, right? So then what they actually do is that, and all the green nodes are essentially router nodes, but they don't per se produce or consume any data. Say any message from here to here can traverse like this, but any message going from, let's say, this node to this node will have to go up, 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 again come down, 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 and this way. So one thing that is obvious is that a lot of messages, right? If you think about it statistically, 50% of the messages will go via the route, right? Because, if we assume that the traffic pattern is random, then, there's a 50-50 probability that a message will be in this half or in that half. So half of the messages will actually be traversing the route. Because of that, the route can be a point of contention. And what will happen is there can be a lot of congestion over here. So think of it this way, there are two cities and then they are going via this bridge. So well, there will be a lot of traffic within the cities, but all the intercity traffic will be via this bridge and this will become a point of contention. So what do we typically do? What we typically do within a city is that if we have 1 lane or 2 lane roads in the city, then this bridge is actually 8 lanes, right? This is a typical thing that is done in cities, that these bridges are very, very wide. So sort of take care of the traffic. Similarly, inside the city also you can have these mini bridges which will be 4 lanes. So that's exactly what happens. That these links are very narrow, but these links can take multiple requests in parallel and they sort of get wider, which means that maybe this link can carry 4 requests in parallel. These links can carry 2 requests in parallel to ensure that we don't have a lot of clogging at the top. So that's the reason it's called a fat tree, because towards the root, the links get wider, which means that they can carry more requests in parallel. So as a result, the throughput of the system does not suffer because there is really no congestion towards the upper nodes, right? So as I said, this network is not very popular inside a chip. It is more popular in a cluster of chips like a data center or a cluster or something where we have a lot of machines. So there we'll have these individual switch elements and the switch elements will be connected with wires, but the throughput of these, the bandwidth that these wires can support and the bandwidth that these routing nodes can support will keep on increasing as we move towards the root. So let's now take a look at one more topology, which is, well, actually, let me go back. I didn't discuss the bisection bandwidth. So the bisection bandwidth is actually when we cut off one of these links. And these links, technically speaking, is one link, but it can contain, since this link is fat, means that it can take in multiple requests in the same cycle. Uh, so, the bisection bandwidth can even be more. And if you consider these as different links, and the diameter is not much, it is basically log n steps till the root and log n steps back to the destination node. So the diameter per se is small. Now let's look at a topology which is most commonly used within on-chip networks because it's very, very easy to implement. It's a mesh. So as you can see, a mesh is exactly a matrix. So we can think of the mesh here as having, root n, a root n by root n, a square kind of mesh. So essentially, it's very, very easy to implement because these can just be adjacent tiles. So any message that is going from, let's say, here to here, this will be the longest path. The longest part of the message will actually go like this and it will go like this. So the diameter is 2 times root n approximately because you traverse root n steps like this and then root n steps. It's an approximate figure. We are ignoring small constants. And the bisection bandwidth, well, so what we need to do is we need to cut off all of these links to, break the network in half. So the bisection bandwidth is also high, right? So the bisection bandwidth in this case is roughly root n, and the diameter in this case is roughly 2 root n, which means it's good. The diameter is fairly small. The bisection bandwidth is fairly high. So this as such, so bisection bandwidth high meaning there are many paths which the request can take to go from one side of the network to another side of the network. So this network having a good bisection bandwidth is a very good thing, and which means that a good throughput can be sustained, and having a low diameter is also a very good thing because it will be so diameter is not as low as the fat tree because that was of the order of log n. This is the order of root n, square root of n. But nevertheless, it's much better than a chain and a ring where the diameter was order of n. So it turns out we can do better than a mesh. So what we can do is, let me just go back. We can connect the ends of a mesh. So we can connect this and this. We can connect this and this. So if I connect the ends of a mesh, so basically both the rows as well as the columns. See, if you see this mesh, you will find that all the rows are connected. This one is connected here. All the rows are connected. Similarly, all the columns are connected, right? So all the columns are connected like this. So this kind of a structure is called a 2D torus. Okay. So the advantage of this is something like this, that let's study the bisection bandwidth and the diameter. So what were the previous values for a mesh? They were root n and 2 root n roughly. So let us compute the bisection bandwidth of this and let's compute the diameter of this. So the bisection bandwidth, it turns out, well, the cut is at the same point. If we cut the network like this, it will get disconnected. But as you can see, instead of cutting root n links, we actually need to cut 2 root n links, right? Because, if you from this cut, there are actually 2 links that are there, right? So, 1, 2, 1, 2. So, we need to cut both of them to disconnect. Again, we need to cut both of these. So, we have 2 times square root of n links that potentially need to be cut. So, the bisection bandwidth as compared to the mesh is actually double, which is a good thing. Now, in terms of the diameters, so what are the farthest nodes, right? That's the most important thing. The farthest nodes are not this and this. That's the wrong answer because within one hop I can reach this. Within one more hop I can reach this. So they are not the farthest. What is the farthest is pretty much a node here and a node in the center, maybe this. So in this case, I need to travel roughly root n by 2 nodes to reach the middle. Again, I need to travel root n by 2 nodes, in this way to again reach the middle. So the diameter is approximately square root of n. As you can see, previously the diameter was 2 times square root of n. Now it is square root of n. So what has happened is the diameter has become halved and the bisection bandwidth has doubled as compared to a simple mesh. So torus in that sense is a much better interconnect. Of course, we are using far more wires, but in terms of the basic properties, which are the bisection bandwidth and the diameter, a torus does much better because its diameter is half of that of a mesh and its bisection bandwidth is twice. But of course, the wire requirement is also more, so those issues are there, and there'll be some more amount of routing complexity. But nevertheless, if a torus can be implemented, it should be done. And in on-chip networks, a torus is implemented. It's not uncommon to actually have a torus. So let's go back to this torus thing once again. So if you see, there is a certain imbalance in the torus. The imbalance is that these links are short. These are short links, and this link from one end to the other is actually very long, right? It's just not long, it's very long. It's root n times longer. Similarly, here also the links are short, right? Here also the links are short, but this link is actually long. It is root n times longer. And this is a problem. This is an imbalance. So this basically means that if a message takes one cycle to go from here to here, it might not take one cycle to go from here to here because the propagation delay is much more. So to remedy this, what is typically done is that we have a folded torus, which has the same properties as the torus, but if you would recall on the link, so let's assume that this is one, so basically this is one column, right? So one column is basically a ring by itself. So if you look at one column here, then all of these nodes were one node apart, and the first and the last were root n nodes apart. But here, if you see, they are actually placed on different ends of the ring. So this is placed on the upper one. Uh, sorry, this is placed on the left one. This on the right half. This on the left half, left, right. Similarly, if I consider any single row over here, so if you see a row in the case of a mesh, all of them would have been just placed close by and there would have been one long link, but that is not exactly how it has happened. So here, this one is on the upper half of the row. This is at the lower half, again upper half, upper, lower. So what has happened is that the distance between two nodes, instead of being, in this case, if I assume that this distance is 1 unit, then the distance between two nodes, instead of 1 unit, has actually become 2 units. But we have avoided that ultra long wire, right? So now everything is uniformly 2 units away from each other, which is fine because that ultra long wire would have created a lot of problems and a lot of imbalance. And it also might have artificially restricted the length of the clock cycle. But in this case, in a single row or in a column, the distance between adjacent nodes is constant, it is fixed. And the reason for that is this particular topology that we have used. So I would like to request readers to stare at this for some time till you can appreciate why it has been done in this manner. So you will then realize that doing this in this manner ensures that we can avoid those ultra long links from the start of a column to the end of the column or start of a row to the end of the row. Otherwise, the properties of a folded torus are no different from that of an ordinary torus. right? Essentially that is an invariant. So since that does not change, let's move forward and take a look at a few more topologies. So let's take a look at the hypercube. So the hypercube and one more topology, the butterfly. Well, the butterfly might still be used in on-chip networks, but a hypercube is more for an off-chip network where we take individual processors and we can use a hypercube configuration to actually connect them in a larger room, like a server room or something. But anyway, the hypercube is a very, very central topology to the study of interconnection networks. So let us define a hypercube of order 0 as a single node. Then let us define a hypercube of order 1 as taking that single node, replicating it, and connecting them with a wire. Similarly, let's take a hypercube of order 2 as we take a hypercube of order 1, two hypercubes of order 1, and where their corresponding nodes are connected with wires, which is exactly what we get. And a hypercube of order 2 is the same as a square. So if we actually start numbering the nodes, so if a hypercube of order 1 has the nodes 0 and 1, so you will see that we first copy paste two hypercubes of order 1, 0 and 1. 0 and 1 are of course connected. After that, what we do is that we connect 0 and 0. Before 1 0 we put 0 0, before the other one we put uh, 1 0, right? 0 before 1 and sorry, 0 before 1 and 1 before the other. And similarly, we connect the 1 and 1, but we have the same numbering scheme 0 1 and 1 1. So if we actually see between any two nodes, there is a difference of only one bit. 0 0 is connected to 0 1 or 1 0. Similarly, between 1 0 and 0 0 or 1 0 and 1 1, there is also a difference of one bit. So we'll sort of generalize this concept. So similarly, for creating a hypercube of order 3, we take two hypercubes of order 2, right? And we connect their corresponding nodes. So basically, this node is the same as this. This is the same as this. This is the same as this. So this becomes a regular cube. As you can see over here, the hypercube of order 3 is a regular cube. And we have done exactly the same thing. We have reproduced two hypercubes of order 2. And their corresponding nodes have been connected. So 0 0 has been connected to 0 0 of one has been connected to 0 0 of the other. In one case we have prefix 0, in other case we have prefix 1. Similarly, 1 1 of one hypercube has been connected to 1 1 of the other hypercube. And for example, what we have had over here is that this 1 1, right, this 1 1 was connected here. In this case we prefixed a 0, in this case we prefixed a 1. So the same property holds that each node of the hypercube is connected to three other nodes here because it's a hypercube of order 3. And each of these nodes there's a difference of 1 bit. So 1 1 0 and 0 1 0 difference of 1 bit, the MSP. 1 1 0 and 1 0 0 difference of 1 bit. 1 1 0 and 1 1 1 again difference of 1 bit. So if we do the same for hypercubes of order 3, we can have a hypercube of order 4, which is similar. We take one hypercube of order 3, one hypercube of order 3, and just connect the corresponding nodes. So in this case, each node will have 4 neighbors, right? So for example, this node has 4 neighbors, this one, this one, this one, and this one. And basically all the neighbors will have a difference of 1 bit, right? So this node will have a 4-bit ID, and each of these neighbors will differ from it. Their IDs will differ from it in only one position. So it is fairly easy to compute the properties of the hypercube. So in terms of bisection bandwidth, the property will basically be that we cut it over here. So the bisection bandwidth is essentially equal to the number of nodes in. So the bisection bandwidth of an HN hypercube, right? The bisection bandwidth of an order of n HN hypercube is essentially the same as the number of nodes of an Hn-1 hypercube. For example, if I were to take this cube and sort of cut it, so I'll have to snap it like this. So I'll be cutting 1, 2, 3, 4 links, which is same as the number of nodes in an H2 hypercube. Similarly, if I take a H4 hypercube, the number of nodes I need to cut is the same as the number of links I need to cut is the same as the number of nodes in an H3 hypercube. Computing the diameter is very easy. In an HN hypercube, the ID of one node actually contains n bits. So if I traverse one link means that one of these bits changes. So the maximum number of bits that can change are n, and this means that the maximum number of links that I can traverse is also n, and thus the diameter is equal to n, right? So these are some interesting properties of a hypercube, but of course a hypercube requires a lot of wires between the nodes, and it's often, so these are called high radix topologies, mainly because the number of wires that it requires, right? But if you actually think about it, so let's look at the number of nodes. And hypercube of order 3 actually has 2 cube nodes, and hypercube of order 4 has 2 to the power 4 nodes. So a hypercube of order n has 2 to the power n nodes. If I say that capital N is equal to 2 to the power n, then the diameter which we computed to be n is actually log of the number of nodes. So the hypercube pretty much has similar properties as the fat tree, where the diameter is only a log of the number of nodes. Unlike a mesh or something, it's not square root of n, but it's a much slower function. It's a log of the number of nodes, which is a fantastic thing for us, which means that any two nodes on a network are at best log n links away. Extremely scalable. Uh, but of course, the number of wires that we require is fairly high. And that's the reason implementing this within a chip is somewhat difficult. Now let us look at a different kind of a topology called a butterfly. The butterfly is far more amenable to be implemented on a chip as compared to a hypercube. And there are different implementations of a butterfly network that you will find for on-chip networks, for NOCs. So let us consider a butterfly of 8 nodes. So in this case, there can be different ways of numbering the nodes. As you have seen, numbering the nodes is important in a hypercube. But we have not done this here in the slides or in the book, but can be and maybe should be done, but that's okay. What we do, but the important thing to understand is that unlike the hypercube, the actual shape of a butterfly conceptually is actually a cylinder, right? So it's a circular, in the sense the network folds on itself. But it's very hard to draw a cylinder, so I've sort of cut the cylinder and flattened it. So basically this node over here and this node over here are actually the same. So these are the same node. So what I could have alternatively done is that I could have just extended this wire and made it connect to this node. I would have removed this and just made it connect over here. But that would have made the diagram very clumsy, right? So I did not do that. What I have essentially done is that I've sort of created for the same node 1, I've created two circles. But mind you, this node 1 and this node 1 are exactly the same. They are not different. They are the same. Okay, I'm repeating it several times because this can be non-intuitive, but hopefully with several repetitions it will become far more intuitive. This diagram will become far more intuitive. That similarly 2 and 2 are actually the same node. We just have drawn it twice to make the drawing look better, that's all. Similarly 7 and 7 are actually the same node. It has been drawn twice to make the drawing look somewhat better. Now, if we consider the network, what we see is that two nodes are connected. So these blue nodes, it follows the same terminology, the same format as the fat tree, where we have two kinds of nodes. So the blue nodes are the ones that both produce and consume data. So these are the data nodes. And then the green nodes here are only for the routing. So the job of these green routing nodes are basically to route data from one node to the other. And but these green nodes do not per se produce or consume any data. They only route data from one end to the other. So the first thing is that we transfer the data. So assume that 4 wants to send a message to 7. So we transfer the data to the switch, right? So that's the first thing that we do. So these routing nodes are also called switches, right? Because they don't produce and consume any data. So from the blue node, it comes to the green node. So then we find the ID of the destination switch, which is 1, 1. So if you see, every switch is connected to one more switch at the same level, right? So if there are n nodes, these n nodes are connected to n by 2 switches, and the number of levels is basically, it can be, it's there in the book. So the number of levels are essentially log n. So at every level, one of the bits changes, but that is again, it will require some more analysis, but the analysis is there in the book, so you can go and read it. So here what we are doing is that we are going from switch 0, 1 here in this column to switch 1, 1 in the third column. So every switch is connected to one more switch at the same level, n by 2 such levels. So, and it is connected to one more switch at a different level, at a different row. So since the first bit MSB of the switch ID is different, 0 is different from 1, so what we do is we take what is called this cross link and come to this switch. So then the first bit becomes the same. Now we take a look at the second bit, and the second bit is also the same. So basically what we do is that we continue along the same path till we reach this switch, and then the message finally goes to 7. Now assume that from 4 we wanted to send a message to node number 6. So in this case, the message from 4 would have gone to this switch 0, 1. The node with switch 6 is 1, 0. So of course the MSB is 0 here and 1 here, so we need to take the cross link. So we will come here. So now at least 1 matches. But then the next bit, which is 1, and the next bit here is 0. So there is again a mismatch. So to make it the same, we need to take this cross link. So we'll reach the switch 1, 0. And from here we will go to node 6. So that's the way that routing happens. And since we can have log n such bits, so there are log n columns. Here all logs are to the base 2. Log n columns and n by 2 such rows of switches. So with having so many switches, routing elements which do not produce or consume data, we can route messages from any node to any other node. So as you will see in the book and also in other relevant references, the bisection bandwidth can basically be computed by cutting the network at this level. And at this level, pretty much there are these cross links between nodes of one end to the other and nodes from this end to this end. And also the diameter for this network is very small. The diameter for this network is basically log n, log n plus minus 1 or 2, depends on how you count. Basically because you have these many columns, and in every step we go from column I to column I plus 1, and the number of columns of switches are limited to log n. So let me now summarize all the networks that we have seen. So we have looked at different kinds of topologies other than the bus, of course, but I'm not including the bus because it is not really an on-chip network. Right? The bus is not a network in the traditional network sense, so that's the reason it's not included. So for we have seen the chain, which is a simple linear chain like a linked list. A ring is a ring. A factory is like a tree, no doubt. But since the root can be a point of contention, as we go towards the root, the links get fatter. What do we mean by a fat link? Basically, it can take more parallel requests per cycle. We can have a mesh, which is the same as a regular matrix. We can have a torus, which is again the same as a mesh, but of course the ends are connected. For each row and column, the ends are connected, right? So the ends of each row and column, will be connected like this. We can have a folded torus where the advantage is that a torus always has, if I consider a torus like this, right? So then, you'll have these long links. You'll have these long links. So the advantage of the folded torus is that we don't have these ultra long links. Instead, nodes are distributed in such a way that the internode distance is more than a torus, but these long links are not there. Then we have a hypercube, which is sort of a generalization of a square and a cube. So an order 2 hypercube is a square, an order 3 hypercube is basically a cube, and order 4 hypercube is essentially two copies of an order 3 hypercube with, adjacent nodes connected. So this is connected here, this is connected here, right, in that fashion. Uh, so then we have looked at a butterfly. Oops, sorry. This should be butterfly. Yeah. So then we have taken a look at a butterfly. So the butterfly essentially is a topology like a cylinder, but we flattened it out. So we have a set of nodes, and so mind you, both sides the same set of nodes, and we have a set of switches, which are essentially routing nodes which don't produce or consume any data. So it's a matrix of switches, and each switch can either send the message horizontally to the right or to another node called a crosslink. So let's take a look at the number of switches. A factory will have n-1 switches, but the rest of the topologies don't have a switch because all their nodes either produce or consume data. And the butterfly will again have n log n by 2 switches. In terms of links, almost all the topologies other than the hypercube and butterfly have order n links, but a hypercube has more links, n log n divided by 2, and a butterfly also has a lot of links, n plus n log n. So we have that many links. That's the reason we can afford a small diameter. The diameter for the chain and ring are of order n. A factory has a much smaller diameter, but again, it's not the best topology for on-chip networks. For a mesh, torus, and folded torus, the diameter is of order of root n, right? And for a hypercube and butterfly, here the diameter is small. So these are a hypercube and butterfly are actually meant for very, very large networks. So both on-chip networks as well as off-chip networks, if the number of cores or the number of nodes is in the tens or hundreds or thousands, then the hypercube and butterfly are the best. The main reason being, yes, we do require a lot of wires, but the end-to-end, the worst case end-to-end distance is still, bounded by log n, right? So then the bisection bandwidth for a chain is really bad. Just snap one link, the entire network is gone. Much better for a ring, but still this is order of 1. For a fat tree, the bisection bandwidth we are seeing is n by 2, where the assumption is the size of each link is equal to the number of leaves in a subtree, if we make that assumption. So as I had said, actually let me clean this slide up. So as I had said, it all depends on the assumptions that we make. So then for a mesh torus and folded torus, the bisection bandwidth is again order of square root of n. So these are sort of in the middle. I would say the chain and ring are at one end of the spectrum. The hypercube and butterfly are at another end of the spectrum. So the mesh torus and folded torus are somewhat in the middle, and they have a order of square root of n kind of complexity. Then we have the hypercube and butterfly, which have a fairly large bisection bandwidth, order of n. And but that's also because, see, since the number of wires are more, It takes more wires need to be snapped to actually partition the network. So depending upon the size of the network and the requirements, so if the network is really small, we can go for a chain or a ring. If it's a moderate size, we can look at a mesh or a torus. If it's an off-chip network, we can consider a fat tree. And if the network is, sorry, torus also comes here. And if the network is fairly large, we should look at a hypercube or a butterfly topology. So this completes our discussion on multiprocessor systems. So now we will discuss storage devices and I/O systems in the next chapter.